Okay, good. Now for the actual interesting part of the last 2 minutes here. That's not necessarily incredibly important. No, actually, no, this is the important part. Screw that. This is the important part. Well, okay, the rest is very important to know to pass this class. This is the part I care about. Okay, and that is this. Why? Why is the opposite of for all statement of there exists statement? How can we prove it? Well, so why does the opposite of for all x and d, p of x, why is that equivalent to there exists in x and d such that p of x? So for finite domains, it's easy. Say that d is finite. So it's going to equal sum d1 through dn. For all x and d, could you think of a different way to write that using symbols we know? Oh, for all x and d, p of x. How about make it real simple? What if d was d1, just had two elements, d1 and d2? What's it mean for all x and d, p of x to be true? Let's start simpler. Let's say we just had d1. D was just this set with one element, d1. For all x and d, p of x, what's that equivalent to saying? Right? If there's only one thing in your domain, right? Saying that for everything in your domain, p of x is true, that's just saying that one thing is true, right? That makes sense, I think, right? So, what if you have two things in your domain? What's this saying now? Well, what's one thing that has to be true?
Isn't it just saying like P D1 and P D2?
Yeah, exactly. A for all statement with two elements, just saying the first one's got to be true, the second one's got to be true. Remember, this is a predicate. So if you plug in any value, you're going to get a statement. So this is a statement, right? So if we go the full way, thank you, Lauren. If we go the full way and say there's like d in elements here, right? That's just saying that this giant and statement here is true. It doesn't matter how many there are. Saying that for all x and d, p of x is true is just saying p of the first element is true, and p of the second element is true, and p of the third and all that. For all is basically an and statement. It's a giant and statement. It's saying all these are true. Does that make sense? Now, there exists x and d such that p of x. What's that saying now?
That's saying or.
Yes. Yes, 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 exactly. For all corresponds to and there this corresponds to or. This one of them's got to be true. This one, or this one, this one, this one. Just one of them. And here they all have to be true. This one, and this one, and this one, and this one, this one. Right? Yes. For all is and, there exists as ors. So, let's think about this. The negation of for all x and d, p of x, that's equivalent to saying the negation of for all, or the negation of p of d1 and all the way out to P of dn. There's a bunch of those and statements strung together. But how do you negate ands? That one guy with a weird name had a good law about it.
De Morgan's.
Morgan law, exactly, right? You use De Morgan's law, and this is not a formal proof, right? Because De Morgan's law we always use with two things, but you can prove it works for more. If you do this for and, you get P of D1 or the negation of P of D2, or, all the way out to, or the negation of P of Dn. But what's this? What's a bunch of ors strung together? What kind of statement is that?
For some.
For some. It's a there exists for some. This is saying there exists an x and d such that not P of x. And we get the same thing if we do that there exists. The De Morgan's law turns the ors into an and then it becomes a for all. So this is why. I mean, this should make sense, right? So for finite domains, the for all and there exists are really just compact ways to write all these ands and ors. That's all it is. They're not really special new things. However, how would you prove this if you had an infinite domain? It's a damn good question, right? Like, because for all of there exists, they have kind of wishy-washy definitions. Like as humans in English, we know what for all and there exists means, right? But as humans in English, we also knew what and or meant, right? But we still decided we needed to define it with a truth table so there's no ambiguity, right? But where's our truth table for all of there exists? Like, where is our actual definition of what this stuff means? Well, here it is. For finite domains, that's what it means. This is the definition. So the for all is defined in terms of and, which is defined by a truth table. Good. The there exists defined in terms of the or, defined by a truth table. Good. But for finite, for infinite domains, it's a different story. And the reason you guys don't have an answer is good, because it's a trick question. The answer is we can't. We cannot prove it to be true with an infinite domain just by using like and or in truth tables, which is why I think I told you in the first day of class, there's like 7 assumptions. There's 7 assumptions, the bedrock of all math. 7 things that we assume to be true, and everything else is built from that. This is one of those assumptions. One of those assumptions is that for all and there exists work in this way. That the negation of for all is there exists, negation of there exists for all. That is one of the assumptions, because for infinite domains, you can't quite prove it. The point is, though, all this stuff is shored up. So that is class. Any questions on all this? Good. So for alls or ands, there exists or ors, basically, and that is where the yin-yang relationship comes in. Cool. Well, class over. Good job, everybody. Thanks for coming. I'll stop recording.